Hello everyone, my name is Vikas Soni, and I welcome you all in the part two of this bit manipulation series. Okay, so in the first video, we talked about the fundamentals of bit manipulation, like what are bit set, uh, what are binary things, and what are the bitwise operators like AND or AND XOR and this thing, and also talked about the observations and the properties in these bitwise operators, and how should we are thinking while solving the question that include these bitwise operators and bit manipulation. In the second part, we are going to talk about some things. Just a second. Okay, so in the second part, we are going to talk about the bit set. Bit set is like mainly used in like it's mainly used in the DP, and to reduce the time complexity you will learn this later. Then the second thing we are going to talk about is using bits using bits as sets. Okay, so like the sets have like the union, intersection, all of the thing. Okay, so we are going to do all of the things. So there is no particular data structure in the C++ or any other language for using this type of set and doing union, intersection, and this type of functions on this. Okay, operations. So there are no particular data structure. So we will have this. We will make this type of set from the bits, particularly bit set. Okay. Then the third thing we are going to talk about in this is some amazing patterns, and this part is my personal favorite one because in this we are going to talk about some patterns and some that are made from some observations that are very important and very frequent in the like competitive programming or some DSA things, but they have not any particular name. Okay, so we are going to talk about them also in the later video, and also we are going to solve some questions. Okay, solve some questions. So this is all we are going to do in this video. So let's start with the topic bit set. Okay. So the first topic of this video is bit set. Now, like what are the bit sets? So let I tell you one problem. Okay. So every one of you knows the DP, right? Let's say not DP. Let's say I just have to. I have I just a second. Okay, let's say I have to maintain some boolean array. Okay, so let's say some array is like this thing, in which it will be something like 1 0 1 1 0 and this type of thing. So this is 1 means 2 and 0 means false, and this is a boolean thing. So you can know that you can either store it as the vector of integers or vector of boolean, but the problem in this is vector of integers, this thing only takes 32 bits to you, right, in your storage. And so like 32 bits for only storing ones and zero is not efficient. Okay, like this 1 0, you can just store this in one bit only, right? Because in one bit it is either one or either zero, so that's it. So in the like 32 bits, in like 32 bits we can store this type 32 booleans, right? 32 booleans. So like all the bits gives us ones and one or zero, right? So therefore, like if some binary number is for like 1 2 3 7 bits, then we can store the 7 booleans in this. Then why we are wasting such space? Okay, why we are wasting such space? So therefore, one intelligent people came and he he introduced the bit set. Okay, bit set, which is nothing but this thing what I was talking, right? That like the 32-bit number can give us the 32 boolean values, right? And we can access them and do all the operations on this. And then we are going to save so much space and also time. You will learn this later. Okay, so now let's say I don't know the bit set thing, but I know that if I have, let's say, array of let's say 40 numbers, right? Then instead of making this something array of 40 integers, I can just do like I store one number here. Okay, I only have two integers. Okay, I know that this bit have 30. This number will have 32 bits, and this number will also have 32 bits. The 31st bit, which is the MSB, will be my, okay, just a second. This the MSB will be my ARR of 0. Then the second bit will be my ARR of 1. Right? I can access like this thing, and I am going to save so much space. Okay, just for instead of 40 integers, I have to store only two integers. So now there is so much space efficient thing in this. Okay, I can store just only this. Yeah, and after these 32 bits get filled, I fill from here, and it will end and something like here. In the end there will be extra space, but we don't care about this now. Right, so this thing bit set solves this problem. Okay, instead of doing all this manually, we use the bit set. So what is the bit set? Okay, what is the syntax of it? So I'm sorry, bit set is like this. So you have to write the bit set and some number here. Let I write here 8 and let's say B. Okay, so now in this what I think is made is that like there is now eight spaces of bits. Okay, 1, 5, 6, 7, 8, and now this is my array made of bits. This will be the zeroth, this will be the zeroth bit, first bit, and like this. Okay, and so this is my bit set. Now I can store the boolean in these bits. Okay, I can store 1 or 0. And how we are going to do our operation in this, let me see. Okay, so when I write bit set, sorry, and when when I write this bit set of 8b only, so all the things in the starting are going to filled by 0. Now let's say I want to store, or I want to access the ith bit. Okay, ith bit of this bi, then I have to do nothing. I will just write this b of I, and by this I will got, if this is 1 I will get 1, and if the ith bit is 0 I will get 0, right? So this is same like array. Okay, there is no much confusing in this. So so we know that default this thing is going to be 0, and while if I want to access something, okay, so let's write here. Okay, for accessing ith bit, this is just b of I. Then let's say how to initialize something, how to initialize this thing, this. So you can just make this by default write this, and all the things are initialized by 0, and also set the bits manually by some loop or something. But there is also another array. Okay, another method, sorry, initialize. So while initializing you can write something like this: bit set of 10 and b of, let's say 3. So now this bit set will be initialized according to the binary number of this 3. What is the binary representation of 3? So we know that 3 is equal to some 0 and 1 and 1, right? This is the binary representation of 3. So this thing is now going to be my array. Going to be my array where the last two digits are going to be 1. This zeroth bit and the first bit it is going to be 1. And all the other till all the other 8 bits are going to be zeros. So that thing I know. I can also initialize this by some string, right? Like the bit set of size 8, and here some string of size 8 10011, something like this, right? So I can initialize also the bit set like this. But what is the problem in this is that this point is going to be my MSB, and this thing is going to be my LSB, right? So this thing, so this point is now my like B of 0, okay? So you have to slightly be careful on this thing, because in the binary numbers the numbers are like this, right? So you have to be careful in making this thing. Now how to modify the values? So like if you want to set some bits, and just B of I dot set, and the sorry, just a small mistake. Mhm. What I'm going to do is B dot set I, and now this ith value is going to be 1. What in the first, I don't know whatever this was, 1 or 0 doesn't matter, but now it will is going to be 1. If you want to reset bit, reset or unset, you will write uh, you will write reset, B dot reset ith bit. That's it. Mm. Yeah. Now if you want to flip a bit, then just B dot flip I. This is going to flip the bit. If you want to like set all bits to 1, set all the bits to 1, you are going to do something B dot set only, and nothing in the bracket. And for resetting, what the okay, and for the resetting all the bits, reset all the bits, we are just going to do B dot reset. So that's all thing to modify the thing. And this was all about the fundamental things of the bit set. Okay, all the functions that are used commonly in the bit set. Now, okay, so there are some other functions too. The other function is like count, counting bits, count bits, which is just how many bits are one, how many bits are one, which is nothing but b dot count, which is going to return us the number of bits that are one. Then also you can do the bitwise operations. Let's say you have some bit set of length 8, and you have two bits A and B, and there are some values. You can do A and B, do A or B, you can do A or B, sorry, you can do A and B, you can do A or B, mm, and you can also do A or B. So let's see by an example. So if my one bit set is something like uh, bit set of length 5, and which is nothing but 10010, and another bit set is this one 00111, and now I do, let's say, some bit set C, and this C is equal to A and B. So now how the AND operation is going to be is like this. So I will have 1101, which is B, I will have A, which is 00111. So now my C will be AND of this. So this two, there is this 0, so this will be 0, there is both are 0, this will be 0. again 0, 1 and 0. So this is doing the AND operation on the bit set. Now there is the last and let's say most important function, which is the shifting the bits. So in the last video we know what are the shifting the bits means. There is the left shift, so something like auto, you can use auto or you can use bit set. Or so let's say you want new A, which is shifting the left, shifting this bit left by 2, right? So now in this what will happen is all the bits will move to left. So if your A was something like this, then all the bits will move to left. So this bit will come here, this bit will come here. Now there is an important thing that the left two bits are going to get lost because there is no space to go anywhere. Okay, so these two bits are going to get lost. So if I do this operation, what I will get in last is this both are lost. This 0 is now at the position 1. This one is now at the position 2 if we are just indexing from left to right. Okay, this thing is at now this position, and the rightmost two bits are going to filled by 0. Similarly, if you do something like this, and do the right shift by let's say 3, and your A initially was something like this, then by doing the right shifting, all the bits are going to shift in the right direction by 3 points. So this will get lost, this will get lost, this will get lost. This will come here, this will on the second place, this will on the third place. And now my array is going to be something like this. 0, 1, 1, and these bits are going to filled by 0. So this is a very important thing. Okay, you will see this in the DP. So I guess that was it for the bit masking. And why bit masking is very important, you will see this in the DP section. Okay, so I guess let's just talk about the DP section now, right? So as we talked about that this bit set reduce the space complexity very much, right? And therefore this is used in some DP. So let's say you have a DP which the states are something like I and j. This is often used in the subset sum. Okay, so you know that manually if you are solving this for the subset sum, what is the subset sum? This is 1 or 0. So this subset sum mean is that from the first I elements, can I make can I make sum is equal to j, right? This is just it, and it stores this boolean 1 or 0. So you know that this is going to be a table of ones and zeros because it is like the 2D DP, and we know that there is going to be so much space. Okay, so in this the space complexity is going to be O into n cross m. This is space, and of course time complexity is going to be also n cross m. This is pretty hectic and very like very heavy thing. Okay, so if like your I value is till 1e5 and j value, the sum value can be till 1e4, then you know that O of n cross m is going to be till 1e9, which is of course will give you the TLE. So we should do something to reduce this TLE, right? To get the code accepted. And that's where the bit set come. Okay. And this thing is very common in the DPA. So there are many questions which will give you accepted only if you use the bit set thing in this. If you do the common thing like just making the DP of integer, you are going to get TLE. But with the bit set, you are going to get accepted. Now, how will you convert this thing into the bit set DP? There this DP comes. Okay. So let's just see the DP table and what is happening with some test case. So let's say the first element we have is this 2. This is our AR, okay? And we have to count for the subsets in this. Then the other thing is 5, and last element is 3, and the okay, that we have only 3 elements. Now how the DP will look like? How the DP will look like? So let's say this is our DP table, okay? And oh sorry, I should not make this like I don't make this like this. So let's say when I is equal to 0, I is equal to 0, and this is the section for sum, the section for the sums. So this is like sum is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, this is the section for sum. So when I is equal to 0, this thing is going to be 1. Here, this is section. I should write this somewhere here. Shit. I is equal to 1. So when we are at this first element, we know that we can make sum is equal to 0 and sum is equal to this. All the other elements are 0 because I cannot make sum of this. When I is equal to 2 and this value is 5, what I can make is, I know that for sure what elements I can make in the previous one. I can also make this in here, right? How I just don't take this this second element, and then as I was making the sum in I is equal to 1, I will make it in I is equal to 2. So like that is like clear. Like this thing is saying that I of 1 and 2 is saying that from the first element I can make sum is equal to 2, and this I is equal to 2 will also say that from the first two elements I can make the sum is equal to 2, which is true. That's it. So I know that these values will just move to here, right? And then what I have to do is I have to add 5. So in all of this, like what I'm doing is, let's say I come at this to add this, add 5 in this, and then make this 1. Okay. So like this is the 0th element. So I know that I can make the sum is equal to 0 from previous thing. I will add a 5 into this. And now here at the 5th index, I will get 1. I just remove it. I get 1 here. I get 1 at the 7th place. So can you see here that this thing is nothing but shifting by 5, shifting by 5. So currently I have taken this from left to right, like, but in the indexing, in the indexing of the bits, we know that the bits are from right to left. Okay, this bit will 1, 0, this bit is 1, and something like this. So this is nothing but mm, left the shifting, how which shifting, so left shifting by 5, this that's it. So now at every point what our DP state is going to be like. Let's say our DP state was like this in the beginning. Our DP state was like this in the beginning. Let's call this previous DP. Okay, previous DP, previous DP. Then the new DP is going to be like the previous DP. I just take the previous element. Okay, do nothing. I just have this previous element down to here. I have this previous element down to here. Or or this previous DP mm, left shifted by the w, or this, or AR of I, what is the element at this ith position. This thing is nothing but saying that if I can make this 2, I can also make 2 plus 5, which is 7. So that's it. I will shift whole of the bits by by some value. Okay. So that's it. Let's take some a small test case. Okay. So we have something like 2, then 3. So in the I is equal to 0, the DP state which are 1, 2, 3, 4, 5. Okay, and this thing at I is equal to 0, this thing is 1, and this thing is sorry, this thing is 1. All the other elements are 0. Now when this 3 is added, all the values are going to like right shifted by 3. So like this 5 is right shifted here. This thing is right shifted here. So I'm saying nothing. I'm just saying that if I make this 3, if I can make this 3 from the previous value, so currently I can make this 3 plus 3, or nothing but 3 shifted by 3. Like is this okay to you? Like if I will say that if I can make this 2, then I can also make the 5 here. So that's it. That's the use of this point. And this thing is nothing, just taking the previous TP. So that's it. So now how is going to be save my space. So you know that shifting like this. So let's just take a case of bit set. Okay, what the bit set is storing in us. So let's say for DP, the size of the sum, like the maximum value of sum can be till 8. Okay, so I know that I have to make the like bit set of 8 be something like this, and then for all of the elements I will do this thing. That the new bit set is going to be this and this, or okay. So now how the bit set does this, because we don't know how this test is. Okay, so what the bit set does is it stores in bit of 64, and we know that for each number, we know that this operation can be done into O of n. This thing will turn into O of n. So that is the important thing. And this operation is O of 1 operation. Okay. So therefore, the time complexity and the space complexity will be now O of n into, there was the sum, but now the sum is sum by 64. This thing is happening. Okay. Because I have reduced the sum into 64. I mean, I have in the bunch of 64 thing, and for each number, the thing is like the operation are just two of one. So this is the important thing. So now, in our initial case, like if the n is still 1e5 and the sum is still 1e4, I know that the n into sum, which is 1e9, this will give me TLE. But m cross sum by 64, which is around, let's say, 3 into 1 is 7, this will definitely pass. So that was the use of bits at DP, right? So this was like very important pattern, and you will see some question in the code sources of this type. And like the bit set is very powerful stuff, okay? Because you know that you can just you can just save the space and the time complexity, like reduce them by 64. So that is like very important thing, okay? And it's very powerful. So in case if, and like when to use this. So when we should use this thing is when you have to store, boolean, okay, boolean, and the booleans and the list of the booleans are very big. Let's say that you have to do many operation on booleans, many operation on booleans, or let's say operation in big numbers, like operation in boolean, and this operations, I'm so very bad. These operations can be written as XOR or just like set one bit or something like this. The operation can be done easily. Okay, that is I'm trying to say. So if that is the case, then you know that you are going to save the or you are going to reduce the time complexity by 64. And this is a huge number, right? When you see this. That was the use of bit set, and the main use is just using the DP. I don't have seen some other use of this, like in my experience. But okay, so now let's move to the next use of our bit set, which is having the set having the set bits. Okay, I'm making the set data structure or something like this. So let's say we have some sets, number of set. Okay. Just remove this. So let's say we have some set. One set is something like 1, 3, 5. Other set is like 2 and 4 and 5. And then we have to union them. So we know that in union the set is going to be something like this. But if we do this is going to be the process of O of n, or n where n is the size of this, or let's say O of n plus m, like the sum of this both sides, okay, particularly. So the union, intersection, and the minus, like the subtraction, all of the are going to be of n plus m, because you have to traverse in all of the sets, right? So this thing is going to be O of n plus m operation, but there is other way, which is having sets, as the bit set, okay? Because let's say if the universal set is from 1 to 8, okay, so all the numbers are from 1 to 8, then what you can do is what you can do is making the bit set of length 8 b. Okay, so this thing you can do, or for particularly, let's say this is 0 to 9, and because there are 9 elements, you can have the bit set of 9. Okay, so you can make something like this, and let's say if this zeroth value is going to be 1, if the 0 is present in, I mean the zeroth element is present in this set. Let's just remove this thing, right? So like if the set is something like 2, 3, and 5, this is going to be the 1, 2, 3, 4, 5, and 6, 7, and 8. So there will be some bigger more numbers. Let's say this. Okay. So this thing is going to be 1, this thing is going to be 1, and this thing is going to be 1. All the other elements are going to be 0. And let's say we have some other bit set, other big bit set of length 8, and this set is something like this. Just remove this thing. Now I want to do union of this thing, both thing. Okay. So the union. So can I say that union is nothing but all of this both bit sets, like all of this both element, because union is something like this. So I will have the result in in this set, and if this element is 1 in any of these, then this thing is going to be 1, which is nothing but case of or. So I will just do A or B, which will give me A union B. This is okay, and the union is going to be something like this is 0, this is 1, this second element is 1, and I guess yeah, all are 1. This is nothing but A or B. So just see that very how easy is this. You don't have to make another function like this. No need to make the function for this. No need to make the time complexity of O of n plus m, because the time complexity in this case will be of the size of them by 64, right? So that's it. So that's how. Okay, so you can do A union B, which is nothing but A over B. uh, A over B. Then what about intersection? What about A intersection B? Okay, A intersection B is going to be nothing but A and B, because intersection means that some element should be present in both of the bits, and that's what the definition of AND is, right? So that's it for the intersection. You can do A and B. And how do we find the difference? What if we try to find the difference, which is A minus B? This is the tricky one. So try to think about this. Try to think about this thing. What will be A minus B? So this is nothing but going to be A and this not B. Okay, so how this thing is going to be this. So we know that in this thing, let's say we have something like 1 0 1 1. This is A, and the B is 0 0 1 1. And we know that A minus B in this case is going to be 1 1 0 0 and 0, because A minus B is like. So I hope that you know the definition of A minus B. Okay. So what I am saying is that this thing should be 1 and this thing should be 0, then if and only if, like, right, so A minus B is going to be 1 if and only if this thing is 1 and this thing is 0. So that's what I am trying, right? So this thing is A, and so the I do here is just flip all the bits, flip all bits. So how do we check in this? So if we want to check for A minus B, in this case A is this one, and instead of taking B, I will just flip this thing. So now in this case, this will be not B and this will be A. In this case, I was saying that in this A, that this A should be 1 and this B should be 0, then and only then the A minus B is going to be 1, right? But now if I'm talking about this flipped B, then I can say that this thing should be, and this thing should be, or this thing should be 1 and this thing also should be 1, because it is flipped. So therefore this is the case of and, right? So that's how I will find the A minus B. I hope that you can understand this thing, right? Okay, so there, because the A minus B, let's say what was the bit, let's write the definition. The bit will be one if it is set in A, and let's write unset in B, right? And because I know that there is no way to just write something like this, but I have a AND operation which gives me that this should be set in A, which and and set in B. Okay. So therefore, I just flip all the values of this B, and now my definition will be something like this. And for this, I will use the AND operation. So I hope that everyone understood this thing. Everyone understood the using sets the using sets like in the with the use of bit manipulation, right? And particularly with the use of bit set. I hope that everyone understand that. So now let's also take about some other functions. Like you have to check if some value is present or not, then you know that use a bit set. You can just do something like this and you will find that if the value is present in the B or not in O of 1, right? This is also easy. You know the inserts and deletion and all of these things because we have just talk about them. And also how to check. Okay, I will give you another question. Like how to check. I have some set A. I have some set B. How do we check if the let's A is the subset of B? How do we check this? This is also like good question. Try to think about this. Okay, so this is nothing but what is the definition? So A is the subset of B if all values of A, all value of A is in the B. Is this correct? Is in the B. Is this correct? So like all the values of A is in the B, and let's write something like this. If the A is like this and our B is like this, then we can say that this A is a subset of B. But how do we check this in O of 1 or something, right? For a 1 bit or 1 bit set, okay? One set. How do we check this thing? So this is also easy, right? But the thing is that if you see this carefully, the end of this both operation is going to be A. That's it. So that was just the requirement to check this thing. If this thing is true, then A is the subset of B. So that's it. Now, how do you check if their intersection is not empty? Again, very easy. A and B. You will just count of this, and if this count is zero, then they are empty. So that's it. That's it in the bit set and using the set thing. And this thing can be used in many things, right? You have to store some visit a visit array in the DFS or BFS or using something like schedule thing, right? Where you have some time of something, and you have to see that if you are busy in that time zone or not. Then you have some other friend also. You have to check that in what time zone you are free and that stuff. Okay, so that thing can be easily done by the bit set. So I guess that was it. So we talked about the bit set and there two examples, which was using bit set in the DP and using bit set to make the set, right? The particular set thing. So that was it for the bit set, and now let me move to the my favorite part of the video, which is some important patterns, right? Some important patterns. This is okay. This is the core of this video. Okay. Now, what are the because you know that in this all these two videos we don't talk about any fundamental algorithm or fundamental question types or right because there are not any fundamental algorithms in the bit manipulation, right? So you have to think by step. So what are some important observation and all this stuff? The most important observation in this is this thing. You have to if you have to maximize or minimize one thing, minimize something, you will care. You will only care for the MSB. For the MSB, then the bit MSB minus 1, then only MSB minus 2. What I mean to say is this MSB minus 2 till 0, right? What I'm meaning to say is that let's say there is some number, there is some bit like this, and you have to maximize this value, then you will care only for this MSB for now. Your the first goal should be making this 0 to 1, because you have to maximize this thing, because we know that this is the important thing, that this value is bigger than this thing. Okay, so even if all of the others values, you can make this one, but you are failed to make this value one, then you have failed in this. If you can just set this bit, right? So your main goal should be to set the only first bit, then only. Like if you can set this, then you must set this. Then only you will care about this. Then only you will care about this. Then this, and in last this bit, right? So this is the most important observation in this, that will help you to solve like most of the questions, right? Question. Okay, so let's try to see one question on this thing, and also with this question solving, we will see all the patterns. Okay, so let's say we have this question, and in this question we have, okay, that and is AND operation or is the OR operation, and we are given that array of and length and integer k. You must perform at most k operation, and in one operation what we can do is take some index and replace the ai with ai or 2 raised to power j. So 2 raised to power j is like jth bit. So this operation is to set the jth bit of the element ai. Okay, and the j should be between 0 and 30, and we have to find this value, the maximum possible value of this thing, right? Maximum value of all of the end of all of the values after performing at most k operation. So try to think for this. I will give you a 1 minute. Okay, so let me try to solve this question. Okay, the question is maximal end. The name of the question is maximal end. So let's try to solve this question by taking an example, like taking the test case, and try to see if we can have some observation, right? So let's say we have four values which are something like this. So now, so now, okay, let's make this bit one, okay, and let's say we have k is equal to 2, okay. So and we now the end of this four values is currently 0. Okay, but we know that I know that I can set some ith bit and make it one. Okay, I can set some bit that is the operation. So there are many possible ways where you can use this tool. Like you can set two bits in this. Let's say I set up this bit and I set this bit, but then I will get this value. Okay, I will get the end is equal to 0 1 0 1, or the the other thing I can get is I can do is set this value, and I will get the end is equal to this, right? So what will be the optimal way to choose the numbers? So if you have read this observation that if you want to maximize and minimize something, you will only care about MSB. So what the optimal way should be of thinking should be that you will see only for this element, so that this element MSB, and you will see that you will ask yourself that can I make can I make MSB is equal to 1 in the result. Okay, I mean the value at MSB is equal to 1. Okay, the value at MSB is equal to 1. So you will see that so for to make this one I have to set this weight and set this. Only after that this value is going to be set. So that's it. Now after that, only after I have taken care of this MSB, I will see for this second maximum bit. And again I will ask that what are the operations I have to do to make this bit, the value at this bit is equal to 1. And I know because this is like the AND operation, I have to make this bit also 1. But for that, I will have to do one operation, but I have to do two operations in this, so I don't have any operation left. So I will just going to break the loop or do something, but that's it. So we get the greedy way of traversing, right? The greedy way was if you can make this one, if you can make some bit one, you will definitely make this one. You will definitely do this. So that was all in the code, okay? I mean, that was all in the question. So what we are going to do is you will go at 30th bit. You will ask that how many operations should I do to make this bit is equal to 1? And if you can do that much operation, you will do that much operation and make this 30th bit work. And then you will move to the 29th bit. And that's it in the sorry. So that was it in the question. So let's just move. This was very simple question. Okay. Now the second observation, the second pattern you can say is something like reducing reducing the the possible set. Okay, the possible set, or like matching some patterns. Okay, matching some patterns, right? So now, okay, so that is reducing. So okay, this kind of looks confusing in starting, but this is going to be very easy, and trust me, like the 90%, let's 90% is too much. Let's say 60 to 70% of all of the question of bit manipulation works on this. Will be solved with this. Trust me, this is like I have personally felt this with this. Like so all of the question should be will be just solved by only the observation 1 and this observation 2. So well, just a second. Okay, so let I give you one example with this. So let's the question is something like this that I have. Question is something like this. What? So apologize. I don't know, my pen is why glitching so much. So let's say the question is that you have an array of k elements. Sorry, n elements, and in from this thing you want to take a subset. Take a subset with maximum end value. Let's try to think for this question for a minute. Okay, how we are gonna do this? And okay, so let me think. Okay, so let's assume that in there we have some elements. Let's say the elements are like this. Okay, so we have this much elements, and we want to find the subset of length k is equal to 3. Let's say this thing. Okay, 3. How we are going to think at this question? So again, just get back to the observation one. Going to observation one. What is C for what? Uh, MSP. Okay, MSP. What if in the subset you take for k is equal to 3, the MSB is set. Okay, so like you take A, B, and C, and you do the end of this, and in this the MSB is set. MSB is set. So for that we know that this should MSB is set in all of those three values, right? So we only need to take the value with was the MSB is set. MSB is set in the subsequence to make the MSB is set in the end of this. So in this, let's see that let's say in this, can we take some subsequence with the k is equal to 3 was MSB is set. So you know that I can take this, and this, and now when I do the end of this, and this thing is one, this thing is one, this thing is one. So in my end value, I know that MSB is going to be set. But I can also take this one. So now and then MSB is going to be set in this. But I don't know that exactly which three should I take. I know that if I choose any three from these four elements, my MSB is going to be set. But I don't know exactly which three I will choose. Okay. So this thing, what it does is that it will now reduce my space. Okay, reduce my space. So now I know that if I take only any three of these four values, my MSBs will be set. So definitely and 110% sure that my these three values of the subsequence are 100% from these four values, right? But I don't know which three, but 100% from these three only, right? This thing is this thing doesn't matter, this both. So now my space is now reduced to this thing, this value. Now I have to only care about this thing. So I know that any three value I take from this set, they are going to be with MSB is equal to 1. Now let's say that can I make this bit is equal to 1? Can I do this? I will find this. Okay. So of course I know that if I take only these three values, then my this bit will be also be 1. And I know that according to the observation 1, if I can make some value according to some MSB is equal to 1, then I will definitely make it 1. So now again this value will also get removed. I have only 3 values left, right? And this thing I will do bit by bit, right? If I cannot make this bit is equal to 1, then there will be no change in my this subspace, right? No change in my subspace. But if I can make this value some value is equal to 1, then I know that subspace is going to be reduced, right? Like some elements are going to be deleted. That's it. So until my this space have elements greater than equal to k, I'm going to do my operation. And then after all of the operation, I will just print any of the ko values, right? That's it. So that was the observation 2, that I reduced the possible set to make something maximum or something minimum. Now this matching some patterns or this. So I hope that everyone understood this question. Now let me give you some another question which is around, I guess, 1700 or 1800. I don't remember exactly, but this is like definitely around 1700 questions. So it is going to be pretty tough. Okay. So in this array, what do we have is we have in this question we have two arrays. Okay. One array A of length n and one array B of length n. Now what you can do is you can reorder the values, reorder the array B. Okay. Then the like let's say beauty is A1 XOR B1 and A2 XOR B2 and till like let's say A and XOR B and that's it. And we want to maximize the beauty. We want to maximize the beauty, right? So try to think for this question. Okay, so we have two arrays of length, same length, and you can just reorder this thing, and the beauty is going to be like A's or A1's or B1 and A2's or B2 and till this AN's or BN, and we have to maximize this value. So how you are going to do this? Try to think for this question. This is very beautiful question. Okay, I hope that you have paused and think for some time, right? Okay, if you don't think and just see the solution directly, then there is nothing improvement will happen in it. Okay, so you should try this. Either you get accepted, that's very good, or if you even if you don't solve this question, but you will have definitely some of the observation, or you will have some mistake after seeing the solution, your mistake, and you will find where your mistake was. So just please try this question. This is amazing one. So now let we move to this question and solve this. Let's say we have, let's say you don't see anything, but you know that there is some and so by observation one you will move from MFP to the LSB and try to make the MSB one. If you can do that, very good. Else the MSB will not be equal to one, and then you will move to other values and something like this. But if you cannot take the other observations, right? You should take some test cases in this, and from this test cases, you should try to take some observations. Okay. So from this question, let me try to take some observations that what we can see. So let's have some array A and some array B. And in this array, we have some values like 101, 011, 100, 100, and 100 and let's say 0 1 0. And in the array B, we have four numbers which are 0 1 0 1 1 1 and 1 1 0 and 0 0 0. Okay, these are the numbers. So now you will try to see that for the MSB, like for this second bit, can you can you make this second bit is equal to 1? So for to make the second bit is equal to 1, we know that the operation is XOR. So therefore, to make the some value, okay, some pair, let's say some pair AI XOR BI. To make this thing is equal to 1, AI is equal to 0 and BI is equal to 1, or it should be something like AI is equal to 1 and BI is equal to 0, right? This should be something like this. So I know that. So for this second bit to happen, I know that I have to pair this one with some element with different parity, I can say different parity, or that would be a good word. So I know that if I match this element with this element, then in their XOR, their XOR will be 1 1 1 1 1 1. So this bit is will be 1. I can also, like, for this one, I know that, or let's say for this element, I can either pair it with this one or this element, right? In both cases, the MSP will be 1. Also for this 0, I can pair it with this one or pair it with this one. Like, can you understand this thing? So now for this both element, we have two options in this array, but still we don't know that which element exactly which element I should pair my BI with, right? So that is the case. Okay, so I will just check that can I make this MSB is equal to 1? I will check this. What is the condition for that? What is the condition for that? So, like, for all of the zeros in this, for of the elements which are 0 in the current ith bit, okay, there should be some element with 1, right? So there should be equal number of. So the number of zeros in B in some bit should be equal to number of 1 in A, and also the number of 1 in A or B is equal to number of 0 in B, right? Because you know that there are, let's say there are two elements which have 0, and so there's both elements want to pair with some element which have 1 in the ith bit. Okay, so we are talking about this MSB right now. Okay, so if you're confused, so therefore there should be exactly two pairs, or there should be exactly enough numbers with the proper matching, right? So this is the condition, and if you just, you can check this condition by manually, or the better way of saying this would be the total number of 1 in A and B, also A and B in some bit should be equal to exactly n, which is the size of A and B. So this is, just try to reduce this from this. I am not going to give the proof for this, right? That's very easy. Okay, so now, like, what I will do, what we will do is, let's say in this example, we know that these two elements will get paired in one of these two elements. I don't know which one, right? I don't know if I have to pair this it one or with this one, right? I don't know this thing, but I know that they are going to get paired. So what I will do now is I will reduce the reduce the space, like reduce the options for the this. So, like, what I will write here in the short in the here is, let's say I have two elements which are this from B, and this can be only get mapped with 1 0 1 and 1 0 0. 101 and 100. I don't know exactly what to map, but this should must map with this. If I want to make this MSB is equal to 1 in the beauty, right? And the other two elements, which is 111 and 100, 111 and 100 should be mapped with the these two elements 011 and 0011 and 010. Right, so now we know that now these two are divided into two different questions, right? Or like two new arrays. And this is somewhere like mapping. Okay, so now we knew that I can definitely okay, let's for let's make this thing is equal to okay, what was the this was 0 0. Let's make this thing as 0 1 and this is okay. Now we have taken care of this second bit. Now we will take care of this first bit. Okay. So again, we will ask that if for this bit one, is there some value zero and there is some value zero. There is two options for this, and we will ask for this zero that there are any bit one is in this, so that the XOR will be one, and I will say that there are no for this. So there are no options. So I will say that I can't make first bit is equal to 1 in the beauty, because there is no patch matching in this one. I know that I don't match this with this array like this set. I can't do that. Then the MSB will not be equal to 1. Okay, and I know that I can't interrupt with the MSB, right? The bigger bits. So therefore, I will say that the first bit can't be equal to 1, so I will not do anything. Like, right, because even if I just like pair this with this and pair this with this and break the subarray into two things, but still the first bit is not going to be equal to 1, so therefore why I do that. That's it. Now I will go for the, I will see for the, now zeroth bit, okay. For the zeroth bit, again the pairing is like this, that these two elements should be paired with these two and the two here should be get paired with the other two, right? Now I will ask for the last bit, for the last bit. So for this zero, I will ask that if there is someone in the pairing, which is yeah, and for this one there is this one. In this array there is one for this, so this can be paired with this one. This can be paired with this one, and that's it. So I will get the right pairing. So now my there will be four subarrays. Okay, four subarrays. So this 101 must be paired with this. Must be paired with this 101. This 001 must be paired with this 100. 100. This 111 must get paired with this 010, and this 100. This is 1 must be get paired with this 011. Right. So this is now I get the four different subarrays, right? Four different subarrays. So that was the approach. So if there are some other bits also here, if other bits also, then you will just check for this last bit now, right? We have taken care of this first three bits. I will see for the last bit now. So that is what we have to do in the approach. We are reducing the space for every number, right? We are trying to get the best pairing, right? This is something like this. So that was our second approach, okay? And for using the second approach, there is also the one of the amazing data structure, which is try. We will learn this try in the next video. Okay, this is very useful data structure. This try is also used in the string, and also it is very useful in the bit manipulation. And like in the question with greater than let's say 1600 rating, try is very useful. Try comes very often also. There is also one important concept of Zor subspace, or I don't know what the name was. Yeah, Zor subspace. Zor subspace. This thing is also like very, very important topic, which is this question. With this question, you can find the like the maximum Zor, if some Zor is possible or not, if some Zor is like possible in some subsequence or not, or what is the kth maximum Zor you can get on this thing. Okay, this is like very, very amazing concept for the Zor, and you will also see the amazing properties of Zor subspace. So for this topic also we will talk about this in the next video, and also we will solve some amazing question, pretty hard question in the next upcoming video in the part 3. Okay, so I guess that was it for this video. So in this video we have learned about the bit set and its using in DP. We have learned the using bits as a set, and it's like intersection. Okay, this thing we have learned. Also some patterns, which is like the observation 1, which was take care of the MSB, and observation 2 is was from observation 1, which was just reducing the space or reducing the matching size or something like that. And also we have solved 3 questions. The one was like 900 or 1000 rated, the first one. The second one was around 1200 rated, and okay, this was around, and the third one was around 1700 rated. So that was it for the second video, and we will meet soon in the third video.